Hello everyone, I'm Jens Sander from the Division of Communication Systems at KTH, the Royal Institute of Technology in Stockholm, Sweden. Today I'm going to talk about how we can use the latest advances in signal processing and software-defined radios to largely improve the capacity of HF meshed communication networks. Here's a brief outline of my presentation. First, I will give you some background and motivation for the work, and I will update you on the state of the art of the area. Then I will introduce our new ideas and discuss the concepts of channel allocation and spectrum sharing in HF networks. I will wrap it up with some simulation results that demonstrate the advantages of the new concept and discuss some of the implementational aspects that are at hand. As you may be well aware of, HF propagation is dominated by either the ground wave, which propagates close to the transmitter site, and the long-distance sky wave, and in between there is an area where communication is not possible, the skip zone. The coverage area and the skip zone can be influenced by carefully selecting the frequency. For high frequencies, link distance up to 4,000 kilometers can be covered in a single hop. These long distances also mean that interference can come from very far away, and in particular at high frequencies which are used for the long distance path, the interference situation at the receiver may be very, very different from the interference that you could measure at the transmitter end. Another challenge is the multipath propagation, which is mainly due to mode splitting that results in slow fading and a very limited correlation bandwidth, which severely challenges conventional transmission schemes, in particular if we want to go to higher data rates. If we look at the state of the art of HF communication systems, we have the legacy systems, so traditional technology. This is based on 3 kilohertz channels and mainly due to the compatibility with analog systems for voice, but also due to the limited coherence bandwidth. In recent years, wideband transmission schemes have been introduced. On one hand, we have the so-called single-tone systems, which use a single wideband channel, 12 to 24 kilohertz. These systems have an advantage of having a rather low complexity, but they battle with the difficulty of the frequency selective fading, and also the problem that it may be difficult to find 12 and 24 kilohertz channels which are free of interference. The competing solution that has been introduced in recent years is the so-called HF-XL or Salamandre system. In this system, we use an aggregation of a number of non-adjacent 3 kilohertz channels or waveforms. And by choosing them properly, we can avoid interference and frequency selective fading. The disadvantage here is, of course, that you have a somewhat more complex system, but it's much easier to find multiple 3 kilohertz channels that are free. Another type of technology that is used in modern HF systems is adaptive or automatic link establishment, ALE. These systems automatically select the frequency from a frequency pool by scanning and probing with the intended receiver. And the latest systems use time synchronous scanning. But still, the ALE process is rather slow. Typically, we have to measure for 1 second on each channel. So it takes quite some time to scan through the frequency pool to establish a link. So the total establishment time for a link may be tens of seconds, and that's of course not so nice when it comes to establishing internet connections and with the channel variations that occur. So we have to re-establish several times, which gives a low efficiency. The other problem is that most of the current technologies use narrowband sounding waveforms, let's say designed for 3 kHz, and that's quite difficult if you have a wideband transmission schemes with much wider bandwidth than 3 kHz. And this is typically what the equipment looks like today. In this paper, we're not interested in a single link, but we're interested in a multi-node network where the different communications links in this network have to share the same frequency pool. Trivially, of course, we can assign one or several frequencies to each link, but that's not a scalable solution as the number of links grows with the square of the number of nodes. An interesting opportunity is that we can control the frequency, and by this we can control the size of the skip zone, which makes it possible to reduce the frequency. In the example here on the left, we can see how node 1 is able to communicate with node 8 on the frequency, whereas nodes 3, 4, and 5 are in the skip zone and thus not affected by the transmission. So the interesting research questions we're going to discuss here is how can we design a system that is fully exploits these reuse opportunities, and what are the potential capacity gains that can be achieved compared to legacy systems. The system that we proposed exploits the capabilities of advanced and now quite affordable software-defined radios. For these devices, the entire HF range up to 30 MHz is a quite manageable bandwidth. Receiving and transmitting over the entire range with arbitrary waveforms is definitely possible. Our proposal rests on 2 premises. We will use the channel aggregation of narrowband channels in the same way as HFXL. But the addition that we are able to aggregate channels over the wide frequency range, not only over a few hundred kilohertz, but over multiple frequency bands. The other feature is that we use parallel ALE, where we probe all channels in the frequency pool simultaneously. This is an extension of the channel steering concept that was proposed by Eric Johnson in New Mexico. We use a per-message-based probing as illustrated in the figure below, where each transmission period starts with a probe signal P and a probe response from the receiving station. And then the channel selection is done and the transmission of data can start, and finally there's an acknowledgement slot at the end of each time slot. So how is this channel allocation done? Well, we assume that we have M narrowband 3 kHz channels in each of the K frequency bands. And based on probing of all the channels we have done, the best thing, of course, would be to collect all information centrally and assign a suitable set of channels to each link. This is, however, not very practicable nor scalable, as we have very limited bandwidth to collect this information and send it to some central controller. Instead, we will rely on distributed schemes, where each node and its counterpart decide on the channel allocation based on the measurements performed in that particular link, and that's taking into account the current interference and varying channel conditions. We propose a simple greedy channel allocation scheme where each node that has a message for transmission in its buffer will probe all channels that have sufficient low interference levels. Then the nodes assign all channels where a response was received with a sufficient signal quality. In order to prevent channel monopolization, that the first node gets all the channels, we can introduce some limitations, and we can limit both the number of channels the node is allowed to probe and the total number of channels a single node can allocate. Another problem may be that several nodes probe the same channel at the same time for the same receiving station. In this case, the receiving station may not be able to decode anything. We have a collision. And in this case, we use the popular ALOA scheme, where we introduce a random delay until the next probing. So how does such a scheme perform? We have conducted a simple simulation study with the following parameters. We assume that the traffic consists of messages with size 100 kilobits that arrive to the nodes with equal probability, and they are destined to all other nodes with equal probability. We assume that the nodes have a total power that has to be divided equally over the channels that are used in parallel. We get the path losses and the background noise from a EUCAP prediction tool. And regarding the external interference, we assume that each channel is interfered or busy by external interferers with a probability of p, and the power is log normally distributed. And for simplicity, we assume that the data rate can be perfectly matched to the signal-to-noise ratio with a data rate that is proportional to the Shannon bound. And additional details you find in the paper. So let's look at what the propagation conditions looks like in our network. The graphs here show the number of available channels, or the signal to noise ratio that is expected in the different channels for different conditions. The left curve shows the situation in a summer afternoon, and we can see that different links have quite a variety of frequency channels or frequency bands to spread out on, which means that there would be a large number of available channels. Whereas in the right-hand curve, which shows the expected conditions in a winter evening, you can see that the bands are very much compressed, and basically all the links have to compete in a very limited space, which gives rise to limited capacity. So let's look at some capacity results. First, we look at the expected message delay as a function of the traffic load, i.e. that's the total traffic throughput. That's here on the x-axis here. As we can see, the expected message delay for low traffic loads is dominated by the transmission time for a message. This is due to the fact that in those cases the queues will be empty, and an arriving message can be scheduled for transmission immediately. And as the network throughput gets higher, more and more messages need to wait in queue, and the message delay increases. And finally, we reach a critical load, the maximum throughput above which the system is no longer stable. We see here the effect of increasing the number of allowed channels per node, MTX, and the throughput for a given permissive delay, as indicated by the line in the graph, grows linearly or faster with MTX. The system with MTX equal to 5 could be seen similar to a single carrier system. And if you compare this with a system with MTX equal to 20, you can see that there's an order of magnitude of gain in capacity. However, as the number of channels gets more limited in the winter evening scenario, you can see that increasing MTX pays off up to a certain extent, but when we reach, in this example, about 15, there is no more additional gain. This graph finally shows how many simultaneous transmissions that go on the network on the average. The frequency reuse is in the range of 1.4 to 2, which could be expected by a greedy algorithm that results in many channels assigned to a single link. And that, on the other hand, that link then will occupy those channels a much shorter time. Further, we note that many of the nodes are clustered in the south, where the communication between them basically uses the same bands. So that will be also a shortage of channels. These links can, of course, coexist then with the long-haul links, which may use higher frequencies during the day. So let's wrap it up. We see that modern SDR technology is great for HF. It allows for simultaneous transmission and reception of narrowband signals over a wide range of frequencies. Parallel ALE increases the performance of link establishment by an order of magnitude, and it also goes well together with multi-channel, multi-band transmissions. And channel aggregation has the potential of increasing the data rates by an order of magnitude compared to single channel systems. So what about future work? Yeah, channel allocation, we just scraped the surface here, and the question is, greedy a good strategy, or should we allow for more parallel transmissions? Implementational challenges. We are working on a red-pitaya GNU-based radio implementation to test this in a real environment. Multi-carrier power amplifiers is a big challenge when you want to transmit simultaneously many carriers. And time training synchronization is also something that we need to look at. Thank you for listening.